Alright, we're back, ladies and gentlemen. I do want to point out to you that at one time last year, and I won't tell you now for sure how it's done, but I believe one of the calculus students last year figured out a way to not connect the dots on a parametric equation. Figured out a way just to sketch it so that it actually would in fact look like a sequential graph. Don't remember how to do that, but you're welcome to play with it and see what you can figure out. Alright, back here. Let's go back to the slideshow from current slide. And here we go. And one more time now. Now, what about sketching a graph actually in the sequential graphing mode? Now, I will point out to you, the last sequence formula we had was explicit. If you are doing an explicit formula, it is much easier to do that in parametric graphing. If you have to graph a recursive formula, however, it is actually easier to do in the sequence graphing mode. So let me show you how to take care of that on your calculator. Again, we'll go back. No, I don't want to save the drawings. Go back here and let's tell it to delete. And it didn't want to work that time, so we'll try it here. Delete. Yes, we want to delete. And now we're going to go to menu and graph. And this time we're going to go to sequence and do sequence, not custom, just do sequence. Now, our problem was our initial value was 4, and then we increased by 2 every time. So let's go back here. Our initial value was 4, and then we increase by 2 every time. So the way we do that is we say U1, and then open parentheses, and then we'll do n minus 1 to show previous term, n minus 1, and then we want to add 2. So I'll go plus 2 each time. Now again, let's make sure that we have this right. Yes, we are adding 2 every time, and it says that the end value starts at 2, not at 1. And then we hit enter, and you see this one actually does sketch the graph as sequential points, although it didn't actually sketch them correctly, did it? So I'm going to pause the video, see if I can figure out what I typed in wrong. Give me one moment. Well, ladies and gentlemen, it was a very simple mistake, and I'm a very foolish man. If you look here, go back up, I actually put the things in the wrong part. The top one is where you put your recursive formula. The second one is where you put your initial term. So you see we start at 4, and then the next one goes up 2, and then if we were to zoom out, it would go up 2 again and again and again, and that would make your sequence. Just to show you, let's go menu and let's zoom out. And you see there, it just keeps climbing. That's essentially what we've graphed here. Is we have graphed a line with a slope of 2. If you understand that part of the math. Alright, so going back, and let's go on to the next slide. Yes, yes, yes. There's our graph. Let's actually talk about some calculus now. Limits of a sequence now. Ladies and gentlemen, this is not as bad as it may seem. There are a lot of calculus students and former calculus students that cringe when they see the words converge and diverge. To converge means to move towards something. We say that a sequence converges if, as the terms get larger and larger, in other words, you're looking at the thousandth, millionth, 10 millionth, billionth, and so on term, they start to approach a single number, almost like there's an asymptote there. If, ladies and gentlemen, the sequence does not converge, in other words, maybe it's jumping up and down, or maybe it's going up forever, down forever, we say that it diverges. And there are some rules, and I'll let you pause the video and look over those. They are pretty common sense rules. But I do want you to understand those terms of converge and diverge. So on this first problem, or this next problem, let's see, it says determine whether it converges or diverges. If it does converge, what does it converge to? What's its limit? So we begin by graphing the sequence. Now I'll let you pause the video for a moment if you wish and sketch the graph of that sequence. So if you want to do that, pause the video now, come back, and then we'll keep going. Now, this is what I have when I sketch my graph. And you see that it does appear to start leveling off. It's not going up forever, it's not going down forever, it's not jumping back and forth. It does appear to level off. So I would say that this sequence appears to converge. Now, what does it converge to? Well, we'll take the limit as we approach the infinite term n of 2n minus 1 over n. Now, if I were to plug in infinity right now, it gives me 2 times infinity minus 1 all over. That's infinity over infinity. That's bad. But I do know that it approaches 2. Now, let me back up a little bit and just show you how I know that. You see, ladies and gentlemen, here's what we can do. We can split this up to be the limit as n approaches infinity of 2n over n. Well, 2n over n is just 2 minus 1 over n. Now, if I plug in my infinity, this part here goes to 0. And you see it does go to 2. And if you look here, there's 2, and it does appear that 2 is acting like an asymptote for the sequence. That's what it means to converge. Alright, let's do another one. Let's move this up. Determine whether the sequence with the given nth term converges or diverges. If it converges, find its limit. Same as before. Well, again, sketch your graph if you wish. On this graph, this one would appear to diverge. Now remember, we graphed this one earlier, and remember it was bouncing back and forth, back and forth, back and forth. That is a sequence that diverges. It does not go to a single point. Now we also graphed this one earlier, but this one also diverges. Now it doesn't bounce back and forth, but what was it doing? Well, remember, as we kept going to the right, it kept climbing up steeper and steeper. Well, it wasn't steeper and steeper. It was climbing with a constant rate of 2. So both of these will diverge, this one because it bounces back and forth, and this one because it goes to infinity. A sequence that goes to infinity or negative infinity does diverge. Now, we have the sandwich theorem for sequences. And remember, we discussed sandwich theorem for limits very early in this class. So what is the sandwich theorem for sequences? If you have a limit of a sequence A, and that equals the limit of sequence C. In other words, A and C both converge to the same point. And you have another sequence series B that lies between A and C. Well, if A goes to a point and C goes to the exact same point and B is between them, then obviously B has to have that same convergence limit. Alright, show that this sequence, cosine n over n, converges and find its limit. Well, again, if we were just look at this right now, if we were to take the limit as is, it would not work because you would have cosine of infinity, not going to be good. But very similar to what we did with limits early on, we'll start with the range of cosine. We know cosine is between -1 and 1. We divide everything by n, because you see here this was cosine n over n, so I wanted that in the middle, so I divide everything by n. Now, if you were to sketch these, if you were to sketch 1 over n and -1 over n, you see that both of these do approach 0. So this one approaches 0, that one approaches 0. We can only assume then that the one in the middle must also converge to 0. Now there's one other quick point we want to show you, and I'll have to move the screen down, maybe not. It's the absolute value theorem, and it's very simple, but it will come into play for some things that we do later on. If you have a sequence a sub n, and if the limit of that sequence, as it approaches infinity, is 0, of absolute value of that, then we do know that the limit of the sequence itself is 0. In other words, if the limit of the absolute value goes to 0, then the sequence itself must also go to 0, because obviously absolute values don't affect 0. That will come into play a little later. Well, if you heard that little knock, I know the video was paused and no time lapse, but that was knock at the door. I had to deal with that. But ladies and gentlemen, that is sequences. And your homework, the first section, not too bad right there. Hope you enjoy it.